Dear students, in this video we are going to discuss about Einstein's coefficient. It is a derivational part. So now let us get into the video. So as we discussed already, the interaction of radiation with matter, three phenomenon takes place. The first phenomenon is absorption, the second one is spontaneous emission, and third one is the stimulated emission. So for better understanding of this Einstein's coefficients, please watch interaction of radiation with matter. So the process, once again I just explained by means of the diagram. Let me go one by one. So first one is absorption. So the atoms in the ground state absorbs energy and then it will go to the excited state. This is absorption. So the rate of absorption, how we can able to write the rate of absorption. So the rate is represented by R and the transition takes place from lower energy to higher energy. That is energy level E1 to E2. So the atom jumps from energy level 1 to 2. That's what R12. R12 represents rate of absorption from lower energy level to the higher energy level. So this rate of absorption depends on, okay. So before that, let me explain one more thing, that is N1 and N2. What is N1? N1 is the number of atoms in the ground state and N2 is the number of atoms in the excited state. So it depends on the number of atoms. That's what it is represented as population. So the population explains the number of atoms in the different energy states. So now N1 is number of atoms in the ground state and N2 is number of atoms in the excited state, right? So the rate of absorption depends on, first thing, if atoms should be present in the ground state, then only the absorption process will take place. So definitely this process will depend on N1. This process will depend on N1, number of atoms in the ground state. And another thing is the atom gains energy from the external source, that is photon. So that photon I am going to represent as rho nu. What is this rho nu? Rho nu is nothing but density of incident photon. Density of incident photon. So now you can understand what is the rho nu is. Rho nu is the incident photon, density of the incident photon. So the rate of absorption depends on these two factors. One is how many number of atoms present in the ground state and another one is the density of the incident photon. So to remove this proportionality symbol, I am going to introduce the constant which is B. Okay, B 1 2. What is this 1 2? 1 2 is the transition from energy level 1 to 2 and B is the proportionality constant. So absorption proportionality constant and then N1 rho nu. Okay, so this is the rate of absorption process. This I am considering equation number 1. Considering equation number 1, right? So now I hope you can understand what is this rate of absorption and how can we find this. The same thing we are going to do for the remaining two process also. The second one is spontaneous emission. So here it is N1 and this is N2. So what is spontaneous emission? It is the natural process. Once the lifetime is over in the excited state, the atom will come back to the ground state. So the transition takes place from energy level 2 to 1. So how can we write then R 2 1? Here two emissions are there, spontaneous and stimulated. To show this I am writing SP here, R21 SP, which is proportional to. See here, no other involvement of the incident photon, only the number of atom. How many number of atoms? Once they completed the lifetime, automatically it will come back to the ground state. So it depends on N2. It depends on N2. So to remove this proportionality symbol, I am going to introduce the constant which is A and the transition takes place from 2 to 1, from up higher energy state to ground state. So A21 N2. Okay, and A21 is the proportionality constant, spontaneous emission proportionality constant. So R21 spontaneous is equal to A21 N2. It depends only on the number of atoms in the excited state. So this I am considering equation number 2. right? Next we are coming to the stimulated emission. What is stimulated emission? That means the incident photon will stimulate the atom in the excited state to come back to the ground state. By the time two photons will be emitted, right? So here, how to write the rate of stimulated emission? Again, 2 to 1 only. The transition takes place from higher energy to lower energy state, and which is represented as St here, which is proportional to. Now again N1 and then N2. See, it depends on two things. One is number of atoms as well as the incident photon. So incident photon is represented by rho nu, density of the rho nu, and the number of atoms in the excited state, right? So now I am going to remove this proportionality symbol by means of constant. So here B, the transition takes place from 2 to 1. So B to 1 rho nu N2. Okay, and then here B to 1 is nothing but the stimulated emission proportionality constant. Okay, so this is I am considering as equation number 3. Equation number 3. So now you will have the doubt that why in some place I mentioned B, in another place I mentioned A. What is the importance? What is the significance? Now you see, equation number 1 and 3 I mentioned B. Why? Because in equation, that means in the process of 1 and 3, who is involved? Incident photon is involved. To show the incident photon involvement, I mentioned B. In the second case, there is no involvement of the incident photon. That's what the other constant I have mentioned as A. So now what we are going to discuss, Einstein's coefficients. Here A and B are the Einstein's coefficients. A and B are the Einstein's coefficient. Now we are going to discuss what is the value of A and B by using these three equations only. I hope how the equations are derived from the process: absorption, spontaneous emission and stimulated emission. So let us get into the derivation part now. So now we are talking about Einstein's theory of absorption and radiation, absorption and emission. So now this Einstein theory of absorption and emission based on Planck's quantum theory of radiation. Planck's quantum theory of radiation. Okay, so based on that only we are going to calculate the coefficients. And moreover, this is main point we have to remember. This theory based on Planck's quantum theory of radiation. And the second point is, and at a thermal equilibrium condition, at thermal equilibrium condition, the population, who is that population? Number of atoms in ground state and excited state. So the population obeys Boltzmann distribution law. Boltzmann distribution law. How the atoms will be distributed in energy levels. So that is based on the Boltzmann distribution law. So to derive this, to find the coefficients A and B, I am going to follow these two concepts. One is Planck's quantum theory of radiation and another one is Boltzmann distribution law. So let us start the derivation part. Okay, so the first part is, at thermal equilibrium condition, at thermal equilibrium condition, rate of absorption is equal to rate of emission. Right? So as per this, at thermal equilibrium condition, the rate of absorption is equal to rate of emission. We have two types of emission, spontaneous and stimulated emission. So rate of absorption is given by equation number 1 should be equal to equation number 2 plus equation number 3. Equation number 2 gives spontaneous emission and equation 3 gives the rate of stimulated emission. So let me write the values here. Equation 1 value is B12 rho nu N1, right, which is equal to equation 2 is A21 N2, okay, and then plus equation 3 is B21 rho nu N2. Okay, so now you see in this is the left hand side and this is the right hand side. So in this term 1 and 3 we have the rho nu. So now I am going to take this rho nu also to this side, this term also to this side. So let me write in the next page. So what I am writing now, B12 rho nu N1 minus, that is in that side. So B21 rho nu N2, which is equal to A21 N2. So here in this left hand side, rho nu is common. I am taking out of this. Okay, for that the first term will be B12 N1 minus B21 N2, which is equal to A21 N2. Okay, I'm going to keep this rho nu this side, remaining all the terms will go to that side. So rho nu is equal to, it is multiplying here. So A21 N2 divided by B12 N1 minus B21 N2, right? See here, here N2 is there, here also N2. So for my convenience, what I'm going to do is divide by N2 on RHS. Only on RHS I am going to do. So how can I write rho nu is equal to, okay, so here multiply, that means here first term, that is in numerator N2 divided by N2, right, whole divided by, first term is B12, here again N1 divided by N2 minus B21 N2 by N2. So now what will happen? Here N2 N2 cancelled, here also N2 N2 cancelled. So in numerator which is remaining, A21 divided by B12 N1 by N2 minus B21. So this I am considering equation number 4, right? So now you see this N1, N2. What is N1? Number of atoms in the ground state, and N2 number of atoms in the excited state. So based on Boltzmann distribution, I am going to find the value of N1 and N2. So now according to Boltzmann distribution law, Boltzmann distribution law, N1 is equal to N0 exponential of minus E1 divided by KBT, right? And then N2 is equal to N0 exponential of minus E2 divided by KBT, right? Let me explain the terms in this equations. So first one, E1 is the energy of the ground state, E2 is the energy of the excited state. What is KB here? Where KB is the Boltzmann constant. KB is the Boltzmann constant, right? And T is the temperature or absolute temperature. Absolute temperature. Okay, and then N0. So N0 is the number of atoms in the absolute zero temperature. Absolute zero temperature. Okay, so now you have idea about these two equations. So what we have to find out? The ratio of N1 by N2. Okay, so now the ratio of population. The ratio of population, what is that? N1 divided by N2. So what is N1? What is the value of N1? N0 exponential of minus E1 divided by KBT, right? Whole divided by N0 exponential of minus E2 divided by KBT, right? So here common is N0 will be cancelled. Here this is exponential A divided by exponential of B. So how can we write exponential A minus B? Okay, here I will write exponential of A divided by exponential of B. So how to write this? Exponential of A minus B. Okay, here already minus E2 is there. When it goes up, minus of minus E2 will become plus E2. Okay, so here I am going to write the next step. Listen carefully. What is that? N1 by N2 is equal to, okay, exponential of E2 will go up, but by the time it will change as the positive. So E2 minus E1 divided by KBT, right? So this is the value of N1 by N2, the ratio of the population. So this I am considering equation number 5. So now I have to substitute this equation 5 in equation 4. So now substitute equation 5 in equation 4. So what is equation 4? Equation 4 is nothing but rho nu is equal to A21 divided by B12. In the place of N1 by N2 I have to write this. So exponential of E2 minus E1 divided by KBT minus B21. Okay, in the place of N1 by N2 I substituted this value, right? So the next step I am just going to divide. Okay, divide by B21 on RHS. Only on RHS, how I did by N2, the same thing I am going to do for this also. So what is this? Rho nu is equal to, the numerator is divided by B21, okay, and then B12 divided by B21 exponential. Okay, here we have to do one more change. Exponential of E2 minus E1 divided by KBT minus B21 divided by B21, right? So B21 will be cancelled, it becomes 1. And then here E2 minus E1 by KBT. What is this E2 minus E1? E2 minus E1 is the difference between the two energy levels, which is nothing but H nu. So in the place of E2 minus E1, I am going to substitute H nu. So I will write the next step. See here. So rho nu is equal to A21 divided by B21 whole divided by B12 divided by B21 exponential of, instead of E2 minus E1 I am going to write H nu by KBT minus 1. Okay, so now I am going to rearrange the terms for my convenience. A21 by B21, right, into 1 divided by, okay, what is there here? B12 divided by B21 into exponential of H nu by KBT minus 1. So why I have changed it like this means to compare with Planck's theory of radiation. In the beginning of the derivation itself I mentioned this we are going to discuss with Planck's theory of radiation. So according to Planck's radiation theory, rho nu can be written as rho nu is equal to 8 pi h nu cube divided by c cube into 1 divided by exponential of h nu divided by kBt minus 1. Actually, this is the Planck's radiation law. Okay, so now you compare these two equations. So this is equation 6 and this is equation 7. So by comparing equation 6 and 7, I can write this A21 by B21 is equal to 8 by h nu cube divided by c cube. So B12 by B21 become 1 here. There is no value means which is 1. Okay, so let me write in the next page. So according to the comparison, I can write. So now comparing equation 6 and 7, we get, what is the first answer? A21 by B21 is equal to 8 by h nu cube divided by c cube. Okay, this is one result. Okay, and the next one is B12 divided by B21 is equal to 1. Okay, so I can say B12 is equal to B21. Okay, so these two results we observed. Okay, so what Einstein is going to say with this help of these two results, A21 by B21 and B12 is equal to B21. So what is the conclusion he made? That is what important for this derivation part. So now first one, what is this first one? A21, this is the spontaneous emission rate and this is the stimulated emission rate. So the ratio of spontaneous and stimulated emission rate is equal to 8 by h nu cube divided by c cube. 8 is the numerical number, pi is the constant, and h is also Planck's constant, and c is the velocity of light. So the only variable is frequency of the incident photon. So this ratio depends on the frequency of the incident photon, and A21 is directly proportional to frequency. So what is A21? Spontaneous emission. So what he is trying to say is spontaneous emission is predominant. Okay, is predominant when the light is falling on the matter, okay, which will be predominant. Spontaneous emission is predominant. It is directly proportional to the frequency. So rather than stimulated emission, spontaneous emission is predominant. But for laser production, stimulated emission is required. So how to get the how can we make the stimulated emission to be predominant? For that he is saying we have to follow one technique. That technique is called population inversion technique. Actually, as per the concept, spontaneous emission is predominant, but for laser production, stimulated emission to be predominant. To achieve this stimulated emission, we have to follow one technique called population inversion. So in the next video, we will discuss what is population inversion and how it should be achieved. Okay, and the next one is B12 is equal to B21. What is B12? That absorption. So absorption should be equal to stimulated emission. The rate of absorption should be equal to the rate of stimulated emission. So when we pass the light, both will happen. Okay, both are having the same probability only, so both will happen. It depends upon the number. Okay, so if in ground state more number of atom is there, absorption takes place. In excited state, more number of atom is there, stimulated emission takes place. So this is what the conclusion he arrived. Okay, so Einstein said that as per this concept, okay, he said spontaneous emission is predominant, but for a laser production, stimulated emission is required. To achieve the stimulated emission, we have to follow one technique called population inversion. And the next result is the rate of absorption should be equal to the rate of emission. So it is based on the number of atoms in the energy levels. So that part only we are going to discuss in the next video. So go through this derivation part. If you have any doubt regarding any step, please comment me in the comment box. So thank you everyone.